Hello everybody, my name's Peter Knight and we're going to be together for the next 3 weeks doing some practical sessions on very basic techniques in topographic surveying. Now this year, unusually, you'll realise it's been an unusual year all around, but this year, rather than having introductory lectures in the lab at the start of each practical session, I've taken those lectures out from the sessions and I've given you these resources in advance. So watch these videos in advance of each of the practical sessions, and then for each of the practical sessions we'll actually meet up in the car park at the William Smith building and we'll do everything out of doors, so there won't be any indoor activity during these sessions. Now, what I've done is therefore prepare a number of videos for you to watch in advance of each session. The first video, which you've embarked on now, includes this little introduction and then an explanation, first of all, of how the 3 practicals work and what the techniques are that we'll be looking at during those 3 practicals, and then a little bit more detail about the first of those practicals. So watch the rest of this video first of all, and then when you're done, turn up to your practical session later in the week. Now, we're just doing it outside, we're not going to have the introductory lecture on the day, so it is important that you watch and work your way through this video before we start. Then on your day we'll meet up outside the William Smith building in the car park. You'll be working in groups of 4 or 5, so you can pre-organise yourself if you want into a group, or we can sort that out. If you don't have group members already in mind, then we can sort that out when you arrive. You need to bring your masks so that if you are working in close proximity to other people you can have your masks on. We'll provide all the surveying equipment, but you should bring with you a notebook or some paper and a clipboard and a pencil so you can write down your observations in the field. It will also be very useful if some members of your group, so bring along a calculator so you can do calculations including tangent, sine, cosine, those kinds of things, and obviously bring along your weatherproofs, because we just have no idea what the weather's going to be on the day. So bring your sunscreen, but also bring your waterproofs, because we just don't know what the weather's going to be like. So watch the pre-video, then come along and do the fieldwork bit, and then there will also be some take-home work to do, because we won't be going back into the lab after the exercise to draw up the results and make your map from the day's work. That's something that you can take home with you. And in the video that you're watching now, we'll go on and I'll explain the kind of work, I'll explain the work that you'll be doing after the practical session to draw up your map on the basis of your results. So I'll look forward to seeing you in the practicals. In the meantime, watch this video. If you have any questions, just bring them along to the session and we'll sort everything out there and then. Okay, thanks very much.
Hello, this is Peter Knight, and this is the first of 3 sessions on the basic principles of topographic surveying. As it's recording, remember, if I go too quickly for you, you can of course pause the recording and you can go at your own speed. So what we're going to do over the next few sessions is look at some very basic surveying techniques, and even though they are very basic, they underpin all the more sophisticated types of surveying that you might encounter later on. Surveying is possibly the most fundamental of geographical techniques. You can't really have geography if you don't have surveying. And it doesn't apply just to physical geography or just to human geography. It applies across the whole range of geography. Anything that involves making a map, using a map, measuring distances, looking at distributions, looking at positions or locations of things, distances between things, all of that is fundamentally based on surveying. So it's a really important area for us to know something about, but the basic principles are really quite simple. So what is surveying? At the most basic level, surveying is simply measuring the ground surface. We look at the world around us, we want to measure how far apart things are, we want to plot things on a map, we want to make a cross-section. Well, that's what surveying, topographic surveying, is all about. And it's used for making maps, making cross-sections, finding out distances, measuring the heights of things, the positions of things, the distributions of things. So all this information, this geographic information that we use as part of our programs, surveying is at the heart of that. Geographic information systems are using data that was collected by some form of surveying in the first place. So this is really fundamental stuff for geography. Surveying can be reduced, if you like, to simply 3 sets of measurements. Whenever you're doing a survey, whenever you're measuring material to make a map or do a cross-section, any of these things, there are really only 3 things that we're measuring. Imagine that you're standing in one particular location, so there you are, sat at your desk or standing in your room or out in the field, and we want to measure where everything else is relative to us. For each point that we're finding the location of, we just need these three things: the direction, the distance, and the elevation or the height change, the vertical displacement from us. Whatever kind of surveying you're ever doing, it boils down to just that. So if you get confused at any point about what it is you're trying to measure or how your bit of equipment is meant to be working, what it's meant to be doing, just remember, those are the things that it's measuring. So for example, if you want to know direction, well, once you know where north is, well, then you can count in degrees clockwise from north through north, east, south, west, or by degrees 1, 2, 3, 4 to 360 degrees clockwise from north, and that tells you the direction of something. The distance away that something is, well, you measure that in meters or kilometers or whatever it might be. If you're doing huge measurements of items in the universe, you'll be using light years, but the same principle would apply. There's a direction and there's a distance. When we're doing topographic surveying on the Earth's surface, then we also need to know about height differences. Are things at the same elevation as us? So if you're stood at sea level on the beach, the ship out at sea, well, that's at the same elevation above sea level as you are. You're at sea level. Whereas if you're looking up the hillside to the lighthouse on top of the promontory, well, that's higher than you. The seabed is lower than you. So we also measure elevation changes, plus 2.45 meters in the case of this example I've drawn on the screen here, that I'm at A. I've got an object or an item which is 40 degrees clockwise from north, 248 meters away, 2.45 meters higher above sea level than I am, and that's where point B is. So whatever kind of surveying we're doing, direction, distance, and elevation is all that we're measuring. Today we're going to talk about a particular technique called a traverse survey. Lots of different kinds of surveying you can do. We're going to learn three basic techniques. Today it's traverse surveying. There are various stages to doing the survey. One is to go out and collect the data. Second is to, well, what we call reducing the data. That's what surveyors talk about, reducing their data. What they mean is they're just doing the sums, doing the working out. That's step 2. And then step 3 is using that calculated data, the reduced data, using it to make the map. So there's a fieldwork element, there's a calculations element, then there's a cartography element, if you like. So one of the interesting things, one of the difficult things in a way, about traverse survey is that it separates the data collection from the map creation. Other techniques that we'll be looking at later on, like plane tabling, they do them all together. So with a plane table map, it isn't a case of collecting data, working it out and drawing the map. You simply create the map there and then in the field as you're collecting the data. It all happens in one operation. But traverse surveying, there are several stages to it. But when you do a traverse survey, you traverse the landscape. You start in one location and you work your way across the landscape, measuring as you go. So in this diagram, what we have is a cross section of a hill slope, a little dip, another hill, and down on the other side. And we've started at one end of our traverse line, point 1, and we've worked our way over the hills, measuring as we go. And you can see here what we've measured. First of all, we've got the direction. Remember, everything is distance, direction, and elevation or height change. So we've got a direction. We're going 32 degrees east of north. And then for each little section of the hillside, where there's a break of slope, we remeasure, break of slope, remeasure, break of slope, remeasure. For each section, we measure the length of the hillside that we've walked up, 8.5 meters. And we've also measured the gradient that we're walking at. So here we're going uphill at 16 degrees for 8.5 meters. Then the slope flattens out a little bit. And so we've now recorded a new gradient here, 7 degrees. And we go 4 meters at 7 degrees to 0.3. Then we're going downhill a bit, so again we make a note that we've got to that point, and then we carry on and we go another 15.5 meters, but now downhill minus 5 degrees. Then 19 meters uphill at 14 degrees, then 9 meters downhill at 8 degrees. And you'll notice, this is important later on, each step of our traverse, we do all the measurements separately. So we've got 8.5 meters here, then we have another 4 meters here. That 4 meters isn't a grand total, it's step by step, the local step gradient and the local step distance. And we work our way across the landscape measuring those distances and directions. The distance we might measure with a tape measure. In the old days they used a chain, which is why we sometimes refer to this as chain traverse surveying, but you can measure distance using a tape measure. And the gradient you'd measure using some kind of clinometer, such as an Abney level. And that's an Abney level, in case you've never seen one before. We've got lots of these in the department. You look through one end, and when you look through it, you see both the view out of the other end, and also through a mirror you see up to a spirit level bubble, which is built into the machine there. And so as you tilt the machine looking at higher objects or lower objects relative to yourself, that spirit bubble moves, and you then read off the gradient that you're looking uphill or downhill off this little scale on the side there. Now, we've measured so far the distance up a hill slope that we've gone and the gradient that we've been going. But if you're trying to make a map, you don't put those slope distances on a map. Imagine, for example, you had a vertical cliff. Imagine this cross section actually did end in a vertical cliff here. Well, that cliff might be 10 meters high, but when you plot it on a map, it would come out as just a line. It wouldn't be showing up as an aerial feature on the map. It would just be a line, even though it's got all that distance on it. And that's true of any gradient. So here we've measured 8.5 meters up the slope. But if you imagine plotting that vertically, like a bird's eye view down onto a map, that bottom of the triangle line, which is what's actually going onto the map, is going to be slightly less than that longer hypotenuse slope line that you've actually measured. This bottom line, the line that actually goes onto the map, is what we call the HED, or the horizontal equivalent distance. And you calculate the horizontal equivalent distance by simple trigonometry by knowing the gradient of the slope, which you've measured with your Abney level, and knowing the length of the slope that you've measured with your tape measure. You then calculate the HED. In this case, it comes out, as you can see here, as 8.17 meters, and it's always going to be slightly less than the slope distance. That's how you can check your measurements. Your HED is always going to be a little bit shorter than the slope distance. And here it comes out at 8.17, and so if you're drawing up your map of the distance that you've the traverse that you've made, the map distance is this HED, the 8.17 meters. Similarly, using trigonometry, having measured the slope distance and the gradient, and then calculated the horizontal equivalent distance, you can now also calculate how much uphill or possibly potentially downhill you've gone in making that journey. So if you've gone 8.5 meters at 16 degrees uphill, by this calculation here, which again you can copy down and use yourself if you have an assessment on this, you can calculate the rise or fall, the vertical displacement, the height difference. We use all those terms, but the rise in this case is 2.34 meters. So if you started at sea level, you're now at 2.34 meters above sea level. So you measure the slope, distance and gradient, and you calculate the HED and the vertical displacement. So far so good in terms of measuring the traverse itself, but you now have simply a line along that cross section. That would be great if you wanted to draw a cross section, as we've been doing in that previous diagram. But if you actually want to make a map, then you probably don't just want things that are actually along a single line. You'll want things off to the side of the line as well. You might see a tree off to one side, or a building off to one side, or a sheep that you want to plot on your map, whatever it might be. And we do that in a traverse survey by making offset measurements. So we have here the line of the traverse itself from A, or from the starting point 1, 2, 3, 4 to your finishing point along that north 32 degrees east line of traverse. So you've measured all those points, so you could draw them into a cross section. But suppose there was a feature off here or a feature off there that you wanted to include. The way that you do those is by finding the point along your traverse from which it's a 90-degree angle out to the feature that you're interested in. And then from that point, you again measure the distance and also the slope gradient from the point on your traverse line out to the point that you're interested in. You can then calculate the horizontal equivalent distance of that slope distance that you've measured, and you can calculate the rise or fall between that point, and that then enables you to plot that offset position, your sheep, your tree, your building, onto your eventual map when you come to draw it up. If the thing that you're interested in was off to your left as you were walking along the traverse, well then obviously you're going to plot it off to the left. If it was down to the right from the line of your traverse, then obviously you'll remember to plot it down to the right. So you're collecting lots of information out in the field, which eventually is going to turn into a map like this. You're going to need to record that while you're collecting it. So how does that work? How do we do the recordings of all this data? It's important that you log the data in a particular way. The reason it's important, well, two reasons it's important. First of all, you could confuse yourself later on when you're looking at your own information if it isn't clear. But secondly, like we said earlier, with a traverse survey, people often have one person out there collecting the data, or one team doing the survey. Then they hand the data over to a different team of people back in the lab who are going to do the calculations. And they might then hand the data and the calculations over to a third set of people who are going to be actually making the map. It's really important that all those sets of people communicate correctly and accurately and understandably with each other. They do that by making sure they're all using the same language. So we all have to follow the same conventions for doing the logging of the data and the transmission of the data. And this is something that I might pick up in the assessment for this module, so pay attention to this bit particularly. So the way that you would log this data is on a blank sheet of paper. You're going to start at the bottom of your sheet of paper, and you're going to have a column going up the page from the beginning of your survey, which is down here at the bottom, up to the end of your survey, which is going to be up there at the top. And you begin by drawing a column up the page. And if any of you, the geologists among you, might have seen it, noticed in some of the field notebooks that you use, they come pre-prepared with a column drawn up the middle of the page. This is what that's for. It's so that you can log your survey starting from the bottom and working the way up. You'll notice I've recorded everything on here. So you can see the direction that we're going. This survey was heading off in a straight line direction of 32 degrees east of north. So you look north and then clockwise 32 degrees from north. That's the direction that we're heading off in. We started, I've made a little note here, at the southwestern end of a wall, and the survey is carrying on up until the northeastern end of that same wall, presumably. And then I've logged the information for the traverse in the column, and I've logged an offset to the right of the column here. And I've made notes saying what it was an offset to. It was to a tree that was 5 meters away from the traverse line, down a gradient of 5 degrees from that point on the traverse line. Along the traverse itself, I've logged two sets of information. First of all, I've logged the distance, and secondly, I've logged the gradient. Now, there are various different ways that this can be done. One way you can log the distances as a cumulative distance. Another way you can log it is as individual step distances, as we talked about previously. In this case, notwithstanding the fact that previously I emphasized the importance of measuring the individual distances and the individual gradients, for this log we actually have a cumulative distance. So we've laid a tape measure along the entire length of the traverse, and we've simply read off the reading on the tape measure for each of the points that we've reached. So we went from the 0 meter point, the start of the tape, to 8.5 meters, going uphill at 16 degrees. We then went that additional 4 meters to the 12.5 meter mark, going uphill at 7 degrees. But I've logged that on this particular survey as a cumulative distance, the 12.5. We then carried on all the way to the 28 meter mark. So you need to be careful in your survey, and you could criticize this log because it doesn't say cumulative, cumulative, cumulative. You need to be very careful when you're logging your data, if you do this exercise, that you record what kind of data collection method you've been using, cumulative or stepwise. To illustrate the complication of that, in this particular example, the distance has been recorded cumulative, but the gradients, of course, are step by step. So it's 16 degrees uphill from that point to that point. The 7 degrees uphill is from that point to that point. The -5 degrees is from here to there. So you need to keep your wits about you and make sure that you know exactly what the data is that you're recording, or if it's somebody else's data, make sure that you know what it is that they've recorded before you start drawing the map from it. The next step, having collected that data, is to reduce it or to do the calculations. And the one way of doing that is to begin with your raw data column, which I've copied out here on the left-hand side of this table, and then add a couple of extra columns in which you do the calculations. So if you take some time, pause the recording and have a good look at this diagram, you'll see that all I've done here is step by step, I've taken my gradient and my slope distance, and I have calculated the horizontal equivalent distance and the rise or fall, the heights above the start. And you'll notice here that I have written on the column heads, I've calculated out cumulative distances. So even though the tape measure read 28 meters at the end of my uphill and downdale survey, by the time I account for the slopes and the gradients, we really only went a map distance, a horizontal equivalent distance of 27.5 meters. And this is a final cumulative rise or fall of 1.5 meters. I got higher along the way, but then came downhill again by the end. So these are essentially spot heights for heights above my starting point at each of these cumulative distances along my traverse. So from that data, say pause the recording and have a think about it, but what I've done here is convert my field survey data into data that I can next use to make a map. And this is probably what your assessment might be at the end of this unit, is to take some survey data to do this and to make a map out of it. So in this case, a very simple example, the map that we end up with from this data would look like that. This isn't using that actual data, this is just an example of the kind of map that you could draw up from that sort of data. So you could get a very simple map with the locations of your survey, the offsets, and then from the heights you could interpolate contours. We'll say more about contours later on. But this is the final step. You collect the data, you reduce the data with those calculations, and then you plot the data in the form of a map. So you go out into the field and do your data collection. You'd set the tape or the chain, you'd work out the orientation using a compass, you'd measure the distances with your tape, you'd measure the gradients with your Abney level, you'd measure offsets to anything that you're interested in, you'd log that data carefully and precisely, and you'd make sure that you were careful about what was cumulative and what was local. So remember this diagram, you're measuring a step at a time. It might be that you record a cumulative distance, or you could record these individual distances and work out the cumulative values later. But certainly for the gradients, this is really important, the gradients are individual step gradients. So you don't stand here and measure a gradient to there, another one to there, another one to here, another one from here to there, and another one all the way from 1 to 6. You don't do that. You do gradient 1 to 2, gradient 2 to 3, gradient 3 to 4, 4 to 5, and gradient 5 to 6. With that data, back in the lab, you do the reduction, you calculate the horizontal equivalent distance and the vertical displacement for each measurement, and you then use that reduced data to plot your traverse and offsets, and you can then plot those in the form of a map. In a simple low-tech field mapping exercise such as our chain traverse, once you've conducted the survey and now have a set of spot heights, how do you add contour lines? You interpolate or estimate the positions of the contours based on the available data. Ideally, you'd do this in the field where you could look at the landscape. Otherwise, the spot heights are the only data that you have, such as in our example. So here you can see a set of spot heights marked onto the map 97, 98.1. All we've got is spot heights, but we want to add contour lines in between those to show the topography. So let's try adding a 98 meter contour line. Easy one to start with. If that spot is 97.7 above sea level, that one's 98.1. In the absence of any other information with an even slope, you'd expect that the 98 meter mark would be about 3/4 of the way between the 2 points. With this one, that's at 97 meters, that's at 98.1. So you'd expect about 10/11ths of the distance along the ground, you'd hit the 98 meter mark. Not sure I've drawn that in quite 10/11 of the way, but you get the idea. 98.1, 97.5, where would you estimate as a fraction between 97.5 and 98.1? 98.9, 97.5, well, it's going to be about a third of the way along. Sketch that in. And we're just estimating the positions of the 98-meter elevation in between. We're interpolating in between these different spot heights that we have. 97.7, 98.3, it's going to be about halfway between. I'm only estimating here. When you do your version, you'll do it more carefully, measuring out the distances exactly. The 98-meter spot height, well, the contour line for 98 meters must go right through that one. 97.9, 98.6, about 1/7 of the way along, quite close to the 97.9 you'd expect to encounter the 98. Once you've dotted in those positions interpolated between the spot heights, you can then sketch in, ideally looking at the topography either in the field or on a satellite map, but looking at the topography, try to sketch in exactly where that contour line would go. At the ends, we run out of data. The more data points you have, the better your contouring can be. But with the spot heights that we've got here, that's a rough first sketch estimate of where the contour line would go. Now try it for the 99-meter contour, exactly the same principle. We look for spots in the blank areas between the spot heights where we are estimating that that height would come. So between 98.9 and 100.5, between 98.9, 98.5, 90, this is where you'd look. There you go, here's one, 98.3 and 99.2, so we'll estimate it in there. 98.1, between 98.1 and 99.2, well, it's going to be closer to 99.2. And you can work your way around the map for all the different height levels, estimating, interpolating and drawing in these sketches of where you think the contour lines should go. The more spot heights you have, the more precisely you'll be able to estimate the positions of the contour lines.
Okay, so I hope those introductory videos gave you at least a flavour of what it is that we're going to be doing in that first practical, so it won't come as a complete surprise to you. It will make more sense, I'm sure, when we're actually out in the field doing it. I'll give you a very brief introduction in the field to make sure that you know what you're doing. But the key thing now, I guess, is just let's get out there and have a go. And so I'll look forward to seeing you in your practical session when we can do exactly that. Get outside and have a go at trying out this technique. I'll see you later.